everything. So it's like crap. Okay, so we are recording. Everybody's there, as far as I can tell. Okay, so last week, what we saw, the last thing that we saw last week was to talk about the kind of forces that we can find, and we will talk about spring forces and gravity, weight. What other kind we talk about?
Normal force.
Normal force, and what else? Drag, thrust, and friction. Those are the forces that we were talking about. Okay, so one of the things that we want to do is to look at the effect that forces have on an object. Okay, what we want to be able to do is to be able to identify the forces that we have, and in order to that, to predict what will be the consequence. Is the object going to move? Is it going to stop? Is it going to deform? Is it going to rotate? Okay, so one of the things that we need to do is how do we identify those forces? And once they're identified, how do we find a consistent way to manipulate the forces so we can actually start doing some operations on them, okay? So there are different ways that you can identify the forces. One of them is by the problem itself. So for example, you can have, and I'm gonna switch to the other screen. Now, the people in the online won't be able to see this, but you can have something as simple as an object standing on a table. So imagine that you have just a book standing on that table. Okay, so what forces do we have? Mary.
The normal force.
We have the normal force. What else?
Weight. I don't know if that counts as a force.
Weight counts as a force. Force is the effect of gravity on the mass. What else? Do we have anything else?
Does the pair of forces apply? Even though it's not moving, like the table pushing up and the book pushing down.
Yeah, so we're going to have basically two forces, and these forces are going to appear in pairs. So we're going to have the weight pushing down, and then we're going to have a normal force that is going to be on the surface of the object, on the surface perpendicular to the surface. So we're going to have this normal force. Okay. I didn't say anything. I just gave you an example of putting a book, and then you guys find out that, well, there has to be weight going down. And if the book is not moving, then there has to be something else going up. So that's the normal force. So the problems didn't set up specifically what kind of forces do we have. Okay, think about something like this. We have the same book, the same object. And now what I'm going to do is that I'm going to push the book from one side with my hand, and that book is going to translate to a different position. Okay, so basically I'm just doing something like this. Okay, so what forces do we have? Akina.
Friction.
We have friction. Which way?
Would it just be between, like upward and down between the book and the table?
So we have friction, and the friction is going to go. You can imagine that that's going to happen between the surface of the book, and so it's going to go like this. This is going to be friction. What else? Sylvia?
So wouldn't you also have the weight as a force because the weight you're pushing it
So the weight of the book?
We're still going to have the weight. Kenan?
Thrust?
Thrust? No.
No?
Thrust is a specific kind of force that is basically combustion engines that or propellers, or it's an engine that is pushing you. So no, in this case, no, we don't have thrust. Elizabeth?
We have drag?
Drag, we can also think about drag. The thing with drag is that it only is significant when you are moving at really high speeds. If you are moving at low speeds, friction is going to be way, way bigger than drag, so we can ignore it. When we run, even if you're running, you don't experience much drag. But if you're in a car, and I don't know if you have done this when you were kids or even now that you're driving, if you're driving in a car and then you take your hand out and you feel the wind pushing your hand, well, that only happens when you're going fast. So yes, technically there's drag, but if you are assuming that you're moving at slow velocities, you can ignore it. Okay. Sorry, on the back, wait, on the back. Your name? Annie. Annie. What else do we have?
A force of the table pushing back up on an object.
And we still have normal force. Okay? So same thing as before. We see something that is happening. We see a book that is moving, and you can see me pushing this book. So we know that there's going to be a force of the hand. It's going to be there. There's still weight. There's still going to be a normal force. And there's these two additional forces, the drag and the friction, that even though the problem doesn't specify that those forces are, we can deduct that they happen, that there's going to be there. Okay? So sometimes when you see physics problems, they're going to be information that's going to be very clear. Like you have a person pushing a book with an X amount of force, and that's it. They're going to give you maybe a couple of additional information like the weight of the book or something like that. But then the other forces, like the weight, the normal force, the friction, that they're not going to tell you specifically what kind of forces they are, but you need to figure out that they happen. Okay? How do we know that? How do we know what forces are present? Well, that's why we have Newton's law. So some of you have seen it in high school, some of you have heard of them, but the whole thing of Newton's law, one of the things that we care about Newton's law, is because they help us to identify the problems acting on an object. Okay, that's the whole thing. So I don't want you to memorize the sentence of Newton's law, but I want you to understand why do we care about the Newton's law. So having said that, does anyone remember Newton's law from the first Newton law from high school? And in front of Annie?
No.
Madison.
I don't.
And your name? Brianna.
Was it the one where it's like some object at rest stays at rest and motion stays in motion?
And at rest is at rest, motion stays in motion. Behind Brianna, your name again? Sarah?
Mm-hmm.
Okay. Do you remember anything else?
That was
And
Casey.
Casey.
No, that was what I had.
Okay. So an object in motion stays in motion. And an object at rest stays at rest. Okay, so what Newton's law says in this particular, in the first law, is that this book that we have over here, there are different forces acting on that object. There's gravity, there's normal force. There can also be wind. You can have this on the outside, so there can be wind or whatever. There are different kind of forces. So there are forces on this object. But when you add all the forces cancel each other. So if there's no external force, if there's no net force or net external force, then the object stays at rest. Okay, so that means that every time you see an object moving, that object moved because there was an external force. Okay, that's one of the main applications, the main consequence of forces is that a force is going to make an object move. Okay, that's this part over here. Now, the second part of Newton's law, that an object in motion remains an in motion, it basically says that, okay, if you have an object and that object is moving, that object's always going to be moving in a straight line at a constant velocity. And if that object does something different, like it starts doing in a curve, or starts kind of changing directions, or starts its velocity increases or the velocity decreases, if anything changes, is because there's an external force. So all the forces that are acting on that object are going to be different than zero, and the consequence is that that object is going to change the way it moves. Okay? So that's the whole thing with Newton's law. It helps us to identify forces. So we know if we are describing a motion of something and that object is slowing down, well, there has to be a force. Even if the problem doesn't say it, we know that there has to be a force. If we throw something in the air and instead of moving in a straight line, it's moving kind of like parabola, it's because there has to be a force. And we need to find out that force to describe the problem. The really cool thing about Newton's law is that there's no experiment that you can do where you can observe the first Newton's law, that an object in motion stays in motion. Like the only way you can do that is if you are in space and you have no effects of gravity, and then you throw something and you can see that it's moving in a straight line. But there's nothing on Earth that you can throw or launch or slide that it will move at a constant velocity in a straight line. They're always going to slow down. They're always going to have the effects of gravity. There's always going to curve. So one of the great achievements of Newton is that he was able to discover these laws just by pure logic. So that was kind of cool. Make sense? Okay. Okay, so we're going to try to use Newton's law to try to identify the forces. Some forces are going to be very explicit mentioned in the problem. Sometimes they're not. The next thing that we need to do is to find a way to calculate this net force. Okay. The net force is just basically is another fancy way of saying that we're going to add all the forces that are present in an object. So in our case in our example of the book that is being pushed, well, the net force is going to be the force of the hand plus the weight plus friction plus the normal force. Okay. Sometimes you see it as a summation of forces. So you have all the summation of all the forces, and that's going to be equal to the net force. Okay. Yes.
What's the third one? The
Friction. Okay. Now, because forces are vectors, we need to set up the vectors in our frame of reference, in our coordinate system. Okay. So we're gonna set up our coordinate system, XY. And in this coordinate system, we're going to draw our object and we're going to draw our forces. Okay. Now, right now, because we're just learning how to manipulate the forces, what we're going to do is we're going to create a simplified model of the phenomena that we want to study. So instead of drawing the object, instead of drawing my book here and my frame of reference, what I'm going to do is that I'm going to change whatever object I have. I'm going to ignore the geometry of that object, and I'm going to replace it for a single point, for a particle, if you wish. So if I have an elephant, and it took me a long time to learn to do elephants, so I do them all the time that I can. Although I always mess up this part. There you go. Kind of a sad elephant. So if I want to look at the forces of the elephant, I'm going to ignore completely the shape of the elephant. Maybe that's why he's so sad. And I'm going to say like, no, this elephant is just going to be a single point. If I want to do a bird, I learned to draw birds when I was like 3, and I haven't improved. So, and this is an angry bird. So if you have a bird, I'm also gonna replace it for a particle, and that's it. So this is what we call a particle model. Do you like my bird? If I had to draw an eagle, it's the same, just a little bit bigger and angrier. So instead of drawing this big object, I'm just gonna draw a particle, and the only property that I'm gonna conserve is the mass. So whatever mass my elephant had, this particle is gonna have the same mass. Whatever mass my bird had, I'm gonna have the same mass in this particle. So, and that particle, what I'm gonna do is I'm gonna place it at the center, at the origin of my frame of reference. So I'm gonna put it right here at the intersection of the 2 axes. Okay. Now I'm gonna draw the forces that I identify. And the way I'm gonna draw the forces, remember that I can displace forces anywhere I want on the current system. So as long as I don't change the magnitude of the force, and as long as I don't change the direction of the force, I can put that force wherever I want. So what I'm gonna do is that I'm gonna assume that the object is the source of all the forces. So all the beginning of the force, all the tail of the force is gonna start at my object. So for example, if I have the force of the hand right here, if I have the force of the hand, so I'm gonna put this tail, I'm gonna put it on my object. So I'm gonna do it like this. Yes.
Can you just move the physics book down?
Oh.
Thank you.
Yeah. The normal force, even though the normal force appears in the contact with the floor, because the book doesn't have any dimensions, then it really doesn't matter. And I'm going to put again the tip of the tail of the normal force. I'm going to put it at my object. I'm going to put it like this. Sylvia, you've fallen asleep.
No.
I saw you yawning. I think you even cried. Just kidding. It's okay. Sometimes I also yawn in my own classes. And then you can do the same with the other 2 forces. So try to do that on your own. You have the friction, the force of the hand. You have the normal force. Draw the friction force and the weight. Cool. I thought they were going to draw the elephant. That's pretty cool. I'm gonna switch the lights, so be careful on the back. I think people can see a little bit better. Okay, so you should have friction force like this, and then the weight like this. Okay, and I think I think all of you got it correct. Now, this particular kind of representation of having the forces at the origin, having all the forces coming out of the object, and having the object as a single point, this is what we call a free body diagram. Okay, and every time we do a physics problem, the first thing that I'm going to ask you to do is to draw the free body diagram. This is one of the most fundamental parts of any physics problem. The idea is you do the free body diagram, you identify the forces, and then you use that diagram to write down the equations that need to be solved. So if your free body diagram is wrong, then your equations are going to be wrong, and you're going to get the problem wrong. Now, most people tend to skip this part because they think that it's kind of easy and it's kind of silly and it makes no sense. But I can guarantee you that most people that have a physics problem wrong is because of this. The algebra, the math is tedious, but once you start getting used to it, it's just repetitive and then you can get it. But this, if you get this wrong, then everything is going to be for nothing. So I'm going to be like a very annoying, and I'm going to ask you to do the free body diagram every single time. Okay? So far, so good? Okay. People in the chat, if you have any questions, just write down on the chat, please. Okay. So let's do a little exercise. So you have a wall and you have a book, and then you hold in your book with your hand from the bottom. Okay, so you are basically doing this. Okay, you're pushing up and you are preventing this book from falling down. So I want you to draw the free body diagram. The weight always goes that way. Yeah, unless you're in a weird situation like in space or something, you can always assume that the weight's going to go down. So Kenan, Sarah, Madison, Elizabeth, Mary, Morgan, Casey, Emma, Sylvia, Casey, on the back, Casey, Rihanna, oh, come on. Annie, okay, sorry. Okay, so, Rihanna, yes, right? Okay, I got it. What forces do we have?
We have weight.
Weight.
Going down. And there's a normal force going off the wall.
Do we have a normal force? In this case, the normal force, remember the normal force is always going to be perpendicular to the surface. So we're going to have the force like this. We have the force of the hand. That one is kind of explicit there. Anyone else? We have friction. And here the friction is kind of tricky. So if you assume that the hand is pushing the book up, then the friction has to go down. So assuming hand is moving the book up. Okay. If you assume, for example, that the book is really heavy and the hand is only slowing it down, and the book is actually moving down, then the friction will go in the opposite direction. But if we assume that it's a normal book and you are kind of pushing, then the friction is going to go up. It's going to go down. Sorry. Now your free body diagram then should look something like this. So you're going to have, oops, normal force. You're going to have the weight. You're going to have the force of your hand. And then you're going to have friction also pointing down. Yeah. People online, did you guys got it correct? Does it make any sense? Kind of weird because I don't see anything and I'm just waiting for them to write. Okay. Yeah. Any questions? Okay. Now this one, it's tricky. So you have a piece of furniture. It's a tilted plane, and you are pulling it with a rope. Okay, so give it a try. Do the free body diagram. Yeah. You got it? At all? That's good. Okay. I think most of you got it almost there. Okay. So this is a tricky question. So, wait. I know your name. Well, no, I don't. But I know who you are. Wait. Madison. Yes. Okay, what forces do we have?
We have the normal force on the furniture.
Normal force, like this way?
No, like perpendicular to the.
There you go. Normal force. What else?
We have the weight going down. Perpendicular to the.
No, just going down, just straight down. Sarah. You have the force of the rope. So because it's a force, because it's a force given by a rope, we call it tension. That's going to be like that. And wait, I know the names. Well, I don't. Casey.
Force of friction.
Yeah. And then you have the force of friction that is somewhere around here. Okay. Anyone else has an additional force? Okay, so you should not. Those are the main four forces that we have. So now what we need to do is to draw the free body diagram. And in order to do the free body diagram, I'm going to do X and Y. And this is what most of you did. So I have X and Y. I'm going to have the force of weight going down. And then you have the rope, sorry, the tension. Then you have the normal force. And then you have friction. Right? That's what I think most of you did. Okay. And it's not wrong. Okay. You have all the forces and you set up the forces in a frame of reference, and that's all you need. And it's fine. Now, there are some frame of reference, and a frame of reference is kind of arbitrary. You can pick any frame of reference that you want. So sometimes it's better to pick a frame of reference that helps you to manipulate the math of these problems. Okay. So what I do usually is that I'm going to tilt my frame of reference. And I'm going to tilt it in such a way that the x-axis is parallel to the surface. Okay. So in this case, I'm going to tilt this frame of reference. I'm going to tilt my axis, and I'm going to tilt my axis so that the x-axis is parallel to the floor. Okay. So by doing that, the tension is on the x-axis, the friction is going to be on the x-axis, normal force is going to be on the y, and then the weight is going to be somewhere in the third quadrant. So on the new frame of reference, I'm going to have tension along the x-axis, friction along the negative x-axis, normal force along the y-axis and weight somewhere on the third quadrant. Okay. Why do I do that? Well, a couple of things. On your first case, remember something that we need to do is we're going to have to add all these forces. And the only way that we can add them is by decomposing the. If I have this problem, okay, is one, I need to decompose 1, 2, 3 vectors that I need to decompose. I don't need to decompose the weight because it's already on the y-axis, so all the forces along the y-axis. So I need to decompose 3 vectors, which is not difficult, but it can be kind of tedious. On the second case, I only need to decompose 1 vector, the weight. The other 3 are along the x and y axis. So I don't need to do anything with those. So the only thing that I need to manipulate is this one. So the math is the same, it's just that I used to do it once here instead of 3 times. That's the only reason. You get the same magnitude, you get the same vector, you get exactly the same results. It's just that you're gonna do it a little bit faster here. That's it. Okay? Make sense? Okay. So we'll do a quick example now. And let's say that you have a little kid. Okay, I can stop you. So you're looking at the head of the kid. And is being bullied by 3 mean kids and is being pulled by the 3 mean kids. Okay, and one of them is pulling in this direction, one of them is pulling in that direction, and another one is pulling in that direction. Okay, I'm going to say that this kid is pulling with a force of 100 newtons. And Newton is the unit for forces. And we'll talk about later where it comes from. So forces are measured in newtons. Okay. 100 newtons. This guy is pushing with a force of 50 newtons. And this guy, so this is F1, this is F2. And this guy, we don't know what is the force, but he's pulling in such a way that the kid doesn't move. Okay? Okay? So this is where you need to apply a little bit of Newton's law. So if the kid is not moving, what is the net force equals to? 0. So if the kid is not moving, that means that the net force has to be equal to 0. The net force everywhere. So the net force in the x-axis, the net force in the y-axis has to be equal to 0. So we can say that if we add all the forces in the x direction, these have to be equal to 0. If we add all the forces in the y direction, these have to be equal to 0. Okay, and we call this equilibrium. So in physics, when we say something is in equilibrium, the way we represent that in the equation is saying all the forces in x are equal to 0, all the forces in y is going to be equal to 0. Okay. Now I'm going to draw the free body diagram of this guy. Do it really quick on your own. This is from the top view. So even though we still have the normal force and we still have a weight, it's like going into your paper and out of your paper. So you're gonna have force 1 here, force 2 going up, and force 3. And we don't know what is the magnitude, we don't know what is the direction. Okay? Now, again, you have the normal force and you still have the weight, but they're in and out of the paper, so we can ignore them. You can imagine that the normal force is going to be equal to the to the weight, and that doesn't affect either of these three forces. Okay. So what I need to do is to calculate what is F3. So I'm going to use my equations of equilibrium. So in the x direction, what forces do I have in the x direction, Elizabeth? And what else?
I'm guessing what kind of force?
What? No. What forces do I have in the x direction?
Tension? Is that what you're asking?
Mm-hmm.
No.
So based on the diagram, what forces are around its x direction? One is F1. Anyone? Mary? Power of F3. So remember, F3 is going to have an x component and it's going to have a y component. So the part of the x component of F3 has to cancel F1. So F1 plus the x component of 3 has to be equal to 0. Now, the x component of 3 is pointing in the negative direction. So if this is 100, then F3x is also going to be 100. Well, sorry, I'm going to put it like that, negative 100, because it's pointing in the left side. So this will be the x component of F3. In the y direction, Sylvia, what forces do I have in the y direction?
You have the F2 forces,
Mm-hmm.
but then when you also have the F3 forces, or
Mhm.
just do, okay.
You have F2, and you have the y component of 3. And these have to be equal to 0. Now, F2 is 50. So here, I'm going to end up with negative 50. Mm-hmm. So now I have the x component of 3 and the y component of F3. So now I can calculate the magnitude and the direction, and I'm going to do it. Can I do it here? So the magnitude of F3 will be something like this, and I think it's 111.8. I only know because I did it in the morning, not because I did it in my head. And 3 will be the arctangent of y over x, so it will be 50 over 100. So it will be the arctangent for 1/2, and this is around 26.6 degrees. Okay, so the 3 annoying kid is pulling with a force of 111 newtons at an angle of 26 degrees below the negative x-axis. And the net effect is that that little kid is not moving at all. It's just being suffer, but doesn't move. Yes.
So when we write out like our full answers, is it supposed to be like 26.6 degrees below the negative x-axis, or is that just like understood?
If the way I grade these exams or these problems is that if I know that you are putting, if you're labeling in your free body diagram that this is theta 3, and then you say theta 3 is this, I make sense that, okay, you got it. You can be more specific and say 26 below negative x-axis, and that's fine. But if I can match your diagram with your results, then that's fine. Okay. Any questions? No? So you have gone through 2 days on learning online or being in the online version, and this is your first class in person. So have you been able to follow everything? Yeah? Is going too fast, too slow? Perfect? Oh, wow. Ooh. Okay, so just let me know if there's anything you want me to change, if there's something on the image that you cannot see or the sound or whatever, just let me know. There's nothing I can do with the accent, sorry. I can't. I tried, but I can't. So just let me know if there's anything you want me to change, okay? And I'll do my best, okay? And shall we stay, shall we go? We should go, like right now? It's like 10 minutes for the class to be over. Fine, let's go. See you guys on Wednesday. Okay, guys online, thank you so much. See you when I see you guys.
So number 2, right?